All right, perfect. Okay, thanks for joining the webinar, everyone. I can see that we have some 25 people attending here, so I'm very happy about that. It's really great to see you all. So just a quick introduction of myself. My name is Jesper, and I'm one of the co-founders here at Treble Technologies. I have the somewhat vague title of Chief Product Officer, which means that I'm kind of working with this kind of product development here at Treble on a kind of a bit higher level, and also on a lower level, I can tell you. So I've been with Treble from the beginning in developing this product that I'm going to be showing you guys here today and giving you some training. Since we are somewhat many on this call, I think we're not going to do this type of kind of follow me training session here, but rather I will give a product demo of the Treble product, and I'll try to be a bit try to do it not so fast, so that you can follow along. If some of you already have the product up and running, I encourage you to try to follow along as much as you can. But you know, it's just an encouragement at this point. If you have any questions along the way, you can use the Q&A section here in Zoom. I think that is the easiest way to do this. I would like to, you know, I think I would try to take out, you know, if there's some really relevant questions for what we're talking about just now, then I'll try to answer them. But otherwise, we'll take the Q&A in the end of the session. And we only have an hour here, so I hope we can actually get around to having a good and juicy Q&A session as well. All right, I think that's it for the kind of the boilerplate stuff. Please don't hold back with any questions, comments. Oh yeah, one thing, if you haven't gotten a trial set up or gotten a trial account for Treble yet, I think you can just write. I think you can just write in the Q&A here actually, and then my colleague will try to set this up, or at least just contact us in some way, and we'll just get this set up. If you have already an account, you should have gotten an extension. If you don't have an account, if you didn't have an account, you should have gotten this reset password mail. All right, before we get down to business with the actual product demo, I think it makes a lot of sense to just show you some slides here with some overview of our technology and show you a little bit of benchmarks. Then we'll get around to demoing the product or doing the training. And then I hope I can spend a little bit of time talking about just what we have in store for the future for this. I think that would be very exciting, and end up with some Q&A. All right. So let's just jump into the slides. So Treble Technologies is a rather new company. Me and my colleague Finnur Pint, we founded this in 2020. Back then, a couple of naive entrepreneurs just jumping into it. But since then, we've grown quite a lot, and we're around 35 passionate and brilliant sound nerds on the team. Our expertise is, of course, sound simulation and spatial audio, and we have a mission to simply make the world a better sounding place, one simulation at a time. So here you can see a picture of all the nerds. And you know, I don't know if you can spot Waldo here in the crowd. I'm somewhere back here. Let me just put the pointer up here. Not that it's so important, but we're based in of all places in Reykjavik, Iceland. I can tell you that today is actually not cloudy. It's blue skies, but it's a whopping 7 degrees outside, so summer is coming here as well. All right, but let's dive into the actual kind of meat of this presentation here. So what we built and what I'll be showing here today is kind of the first leg of what we intend to build, which is, as we call it, the next generation virtual sound platform. And you know, it all revolves around having fast and highly accurate simulation of sound. And we've noticed that this has a wide variety of use cases. Of course, what we're talking about here today is focused, and what we have now, what we are doing now is highly focused on room acoustics in buildings. and the design of room acoustics. It's a very important part that this is a design tool that we're talking about here. We have attempted to build something that's light and very user-friendly. And, it should make this design process as smooth as possible. But, under the hood, this is actually the state-of-the-art technology, and it's super powerful. And it's very, we're harnessing the kind of the power of the cloud to be able to do this thing where we make it simple, but, it's super powerful. When we've been building the tool, we've always been talking about this threefold value proposition. And the first part here, it revolves around the actual technology inside, like the deep technology in the engine, which revolves around wave-based simulations. That's kind of the cornerstone in it all, and I'll get more into this. This allows us to do more accurate simulations, essentially. And to do this, we are harnessing the power of the cloud, which gives us scalability, gives us the ability to work with this from anywhere. Basically, you can if you can get to your grandma's laptop, you could probably run Treble on it. And the last leg of the value proposition here is that we've tried to make this auralization or experience of your simulation results very accessible and easy and powerful as well. So if we take kind of a more of an architectural approach to looking at this here, then we have this Treble engine, which is what is sitting in the cloud. And here is this is where all your data is stored. This is where all the simulations take place, and this is kind of where everything basically takes place. And then you have the remote control, which is this browser application or web application here, which I'm going to go into great detail and demoing for you guys. But of course, to be interfacing with the real world, or with the virtual world, you can call it. Then we've taken the approach of building these plugins into 3D modeling tools. And here we've started with SketchUp, where you have this proprietary plugin that you need to install to interface geometry into Treble. Let's dive a little bit more into the simulation technology, because I think this is quite important and quite an important thing to have in place when working with Treble. So as we stated, so here it's a paradigm shift in virtual sound, or in sound simulation for building design, and the cornerstone of it is the wave-based simulation. So I guess some people will ask, what is a wave-based simulation actually? Some people, of course, know this, and it's not a new thing that we've invented. This has been in other industries and in academia for a long time. But the concept of it is that you actually calculate or compute the wave propagation in a medium by computing by solving the wave equation for this. So what we do is we take the air inside the 3D model, we discretize it into very small pieces. These small pieces we can solve the wave equation for, and we combine it all into the final response. This takes into account these objects that you put into the space. It takes into account the complex boundaries, kind of how waves reflect off boundaries and all this. So it's kind of the full the full experience in somewhat. If you can model things, then you will get a very fairly accurate response from this. Of course, this is always going to be a simulation of reality, so we're not completely there yet with like actual all the kind of all the effects of nature in here, but we've gotten damn close. So what we're kind of what has made this possible to do this and to put this into an industrial application is that we've essentially taken this this discretization and solving of the wave equation to the next level by making it a lot faster. So to go higher and higher in frequency for these kinds of simulations, you need to discretize the volume in smaller and smaller pieces, making then you have to solve more and more equations essentially. And therefore, it makes a lot of sense to be hybridizing this with kind of what is state of the art today in room acoustic simulations, geometrical acoustics, where you take a more basic approach in kind of assuming that waves propagate like rays or as plane waves through the space. And this doesn't take into account or doesn't include so much of these wave effects of bending around objects and doing these interference patterns and these type of things. I'll take a little bit more of a deep dive into what this is in the coming slides. So here is a nice slide showing what I was talking about before. We basically made it 100 times faster than what was the state of the art to do these wave-based simulations, and that's what makes this industrially applicable. So just one comment here, in the tool you will see a new concept, which is the transition frequency, and that just simply denotes the transition frequency, or the frequency, where we below that frequency we use wave-based, and above that frequency we use geometrical acoustics. And for all the audio engineers in the crowd here, that for example, with a loudspeaker you have a woofer and you have a tweeter in many cases. And to get these to play together, you have to create these crossover filters, and this is this looks a lot like the kind of hybridization technique that we're using, right? So just some details on the wave-based solver here. We are using what's called discontinuous Galerkin finite element. If you want more details on this, you can look this up. I'm not going to go into details here, but what this gives us is high geometric flexibility. It gives us, high parallelizability of these simulations, which essentially means that the computational effort for the same frequency, if you double the volume, it'll take double the amount of time. So it's just scaling perfectly, essentially. And something for our sake, low memory footprint, that's not really something you'll see, but that's a benefit here. So we are proud of our geometrical acoustic solver as well, and no kind of shaming on that. It does what it does well, geometrical acoustics, and it's really fast. So we're using an image source ray radiosity hybrid here as well, and here the hybridization means that the first reflections in the room is done with the image source methods, and the later reflections, so kind of the tail of the reverb, is done with this ray radiosity method. The image source method we're using is pressure-based, and we can do that because we actually have all of the material characteristics needed. Material is characterized in a way so you can get these phase changes of boundaries modeled correctly with the pressure-based. So this is a low-hanging fruit for us to implement this, and this makes our geometrical acoustic solver actually even state-of-the-art compared to other things. And this material modeling is something that we're very proud of. It's something that we've had to solve to be able to implement this into an industrially applicable package. So to run a wave-based simulation, you need some more surface details. You essentially need the surface impedance, which is not something that's generally available for all materials. Usually you get the absorption coefficients, which is an energy-based metric. So what we've done is we've created a large database, which is in our tool, which has been thoroughly created and thoroughly validated that these materials have these absorption coefficients and surface impedances correspond very well. But we've also created in the tool a fitting paradigm so that you can input absorption coefficients and you can get an estimated surface impedance out of this, which allows you to use these energy-based parameters as well. All right, the last thing I want to talk about here under the technology is this rendering engine, or the auralization engine. So we've tried to make this just as simple as possible. You shouldn't do much extra work in our minds to be able to actually run to get an auralization out. So in this case here, it's just like reviewing the results. You can jump into this straight in the browser and get this immersive spatial audio experience. And I'll get to a demo of this where this would make a lot of sense. And here is just a quote from academia saying that these wave-based simulations really make a difference when when you're also listening to these simulations, which is, you know, in the end, the goal to make a better sounding world, virtual and real. All right, that's kind of the you know, the knowledge part of the presentation here, and I'm gonna just go over a couple of benchmarks here, because, you know, you shouldn't take my word for that this is highly accurate. That's of course a statement. So we've tried to you know, run some benchmarks up against what is publicly available, but also doing our own measurements. And we really highly encourage you to, during a trial period, you know, if you have some spaces that you've measured to a high degree and something that's very exciting for you to get higher accuracy, then please, you know, try this out with Treble, and, you know, just use and abuse it for these types of things. That's very helpful for us to hear these stories, and, you know, it's also great fun. So the first thing here is what is something from this benchmark for room acoustic simulations, which is a public database created from I think it was TU Berlin, of measurements. And in this case here, you can see this is semi-anechoic space with a diffusive pattern laid out on the floor, and we're just measuring here, or kind of the measurement is just a single reflection. And as you can see here, when we simulate this case with Treble, we get a very nice kind of comb filtering pattern here that matches the measurement. Whereas, you know, when you do this with geometrical acoustics method, this is just from the benchmark here, then it has a hard time kind of catching these phase effects of the comb filtering. So I'll just move quickly through this. So another study here that is a public benchmark is from the third round robin of room acoustics, and this is the studio here. So as you can see, this is a rather small space with some complex diffusive pattern on the wall, some complex diffusive pattern in the ceiling, and some windows. So it's a smaller but rather complex space here, even though it's a rectangle. And in these cases, it can be, you know, fairly simple to get like these global, highly global parameters such as the T20. And what we've chosen to pull forward here is the EDT value. And in this case here, we ran the simulation with wave-based up to 710. That's the transition frequency here. And we're still investigating why we're not getting a perfect fit here above. We of course don't stop before we're there. But you know, we see here that wave-based is very accurate in modeling these types of geometric details here, and the kind of first reflection that comes off these. So we're very happy about this result here. Another study we did, this is something we measured ourselves, a small room here that's very controlled circumstances, a concrete room where we placed these type of absorption beds here on the walls. And here you can see these loudspeaker and microphone positions. And in this case, we're using both microphones, but we're also using, what's interesting here is you know, an actual mannequin in here, which is a KEMA in this case. And what we did with this room was we tried to push the wave-based up to as high as we could. So we ran the wave-based actually up to 8 kilohertz in this case. And as you can see, when we run this in wave-based up to this higher frequency, we can just, since we're modeling the impulse response directly, we can just compare the impulse response with the measured impulse response, and it's apples to apples comparison. And as you can see here, we are matching, I would say, phenomenally well with these types of in these types of scenarios. So also here, when you see the frequency response, you can see that we're catching all these room modes that happen at low frequencies when you have a low modal density, and the levels are fairly okay at high frequencies as well. Moving on, just showing some energy decay curves here, where we have a good match, and acoustic parameters here, the T20 and the EDT as well, where we have a good match with measurement. One of the interesting things here, I think, is that when we then do a simulation of this spatial audio of the actual mannequin, then we measure, of course, just the microphone outputs of the mannequin in the space. But in the acoustic simulation, we take the spatial audio, so the ambisonics output, and then we convolve the HRTF of that measured mannequin on here, and then we actually get a great match between these two channels in the space. So this is something that we are, we think is a very good benchmark for that this method is working, and basically our auralization method is working well. Okay, I think I almost spent a little bit too much time here. Let's jump into the product demo. So let's see. So when you start with Treble, you should have gotten an email. See if I can get out of here. You should have gotten an email that where you get some links. And since this is a web-based application, all you have to do to get to the Treble tool is to go to app.treble.tech, and then you're basically in here. You're faced with a login screen, but the app just kind of sits here in the browser. One other link that I would like to show you is the docs.treble.tech. Here we have a knowledge base of some of the stuff that I've already talked about here today. But one important one here is this user guide, which will get you started in using Treble. Here you can see also the link to the app. But I would actually like to start this journey off in kind of where usually this stuff starts, with kind of creating the geometry that we want to simulate. So in this case here, I have installed SketchUp 23, and you need to have a SketchUp Pro license. You of course need to install SketchUp, and I think there are some great examples on how to do that from SketchUp themselves. When it comes to setting up the Treble extension, then you have to go into here, and here is a download link for the extensions. And when you click this, you get this package here, and that's essentially all you need to get started. So then I'm going to pull up SketchUp here. Let's see if I can remove this bar here on top. So when you're on SketchUp, go to the extensions, extension manager, install extension, and then here we should find this somewhere in the downloads. This was the file that I downloaded. I installed this, and that's it. That's what you need to do. That's it. So when you close down the extension manager here, you will see that this icon pops up here in your tray, which is the Treble plugin in this case. So I'm just going to hit this button here, which takes you to Treble. And here you'll also be met with a login screen where you can put in your credentials, and then you should get here. So what you can do from this plugin here is, of course, that you can take the geometry that's in the model here, and you can upload that into the Treble tool. Let me just show you briefly how this is working. I'm just going to go back here. So when you have some geometry in SketchUp that you want to interface into the Treble area, essentially, then you have to open this tags folder here, or in some other 3D modeling tools it's called layers, but it's the same thing. And in here, when you start the tool up with a new model, then you're prompted to create these tag folders, which get created under here. So there's one called Treble, and there's one called Geometry. Under here, you see these different tags that is being created here. And in this case here, I've already set up this model of this, which is one of the examples models that we have. And as you can see, if you select some surface here, it has a tag. Sorry, I'm just moving these zoom things around here. So here we go. So here you can see it has been tagged onto the tag walls, which means that this is how you group this geometry for further processing. One of the requirements that we have to be able to run a wave-based simulation is that the model you have to have here has to have an externally closed shell. I think this is a very normal requirement for doing a room acoustic simulation. You can have these what we call open surfaces inside the space, and boxes and stuff inside it as well. But the external shell of it has to be what's it called? Yeah, it has to be watertight. So we have built a small tool inside of a plugin here that helps you get this done. So if I run this check model here, you will see that when this goes through, it means that the model is okay. If I take this door, for example, and I move it out of the Treble folders here and check it again, you will see that it comes up with an error here. Geology is not watertight. You can click this little feedback thing here, which shows you how there's a hole, so it can flood in. But as you can see here, there is like a small, like a ring here around where the door was, where it's marking this is the edges of your geometry here. So I'm just going to move this back into the doors, check it again, and now we should be good to go. So I'm going to upload this into a new project, and I'm just going to call this if this was a project I was working on with a large office building, this is how we intend this here. So, this would be the office building project. And then we have the physical space that you're trying to model here. Let's just call this office number 1. I'm going to create that space, and then I'm gonna name this as the the model that I'm working on. So the iteration of the design that I'm doing. So let's just call this the initial design. And I can write some description here, but I'm just going to upload this straight away. So now this is being transferred into the Treble cloud. And what you'll see here, you can either click this button here to open in the web client, but you can also just pop open your browser, go to apps.treble.tech. And what you'll be met with here as the first thing is your the dashboard screen. Here you see all your projects and all the spaces underneath these projects. And as you can see here, the office number 1 and the office building project appeared here. So I can click this. I can go in here and I see my models underneath. I can see my initial design is here. So I'm just going to click that, select this initial design iteration here, and then I'm going to open that model, which opens it up here in Treble, and you can see the geometry as we had it in SketchUp. So this is the hierarchy of our modeling here. So from this, I can create a simulation, and I'm just going to write this, call this my initial simulation. And now I'm ready to start setting up this simulation. So in general, the acoustics of a space is depending on 2 things. It's depending on the geometry that encapsulates the air, and it's depending on which boundaries you place there. And then of course you can place sources in different locations in the space, and you can create receivers in different places of the space, so where the sound is coming from and where you want to listen to the sound. We've already set the geometry now. Now we just have to do these last 2 things: assign materials and put sources and receivers inside the space. So I'm just gonna pull this open here. Here you can see these layers that we created in the SketchUp model. And when you select them here, then you'll see which parts of the geometry you'll need to assign materials to. All right, so if we just go briefly through this, or try to go through the process of assigning materials. So when you click here on the assign, here you go, on the assignment of a material here, then you can see this sidebar that we have here is our material library. And there is a couple of different ways to get to the material that you want to get to. You can, first of all, you can filter it here by these different categories. You can of course also just scroll through the massive library and try to find the material, but you can also just type in a search string here. In this case here, I'm looking for something fairly rigid for the walls. So I'm just going to go with a rigid group here, or category. And I am going to say this is smooth painted concrete on these walls. And actually, I only want the outer walls in this case to be the smooth painted concrete. I would like to take, even though this is grouped in one here, I would like to take these 2 surfaces here and make them into gypsum wall. So I can select this. I find it here in the group. Sorry, once again, I'll select this. And let's take a 13mm gypsum board, plasterboard with some mineral wool behind. And I'll select this one as well. And assign this. Sorry, there's a lot of surfaces in this here. Oh, here it is. There we go. So assigning that as well. Then I can fold this back in. There we go. And then kind of moving on to the next here, the floor. I would like to have carpet tiles on the floor. Moving on to the window. Here it makes sense just to take all the glass surfaces. So I'm just going to filter this down to the windows. This is going to be a double pane glass. And here I also have a glass wall, which is just going to be a single pane of glass. I'm going to take that right off the bat here. And then let's talk about the ceiling. And in this case here, I would like to have a porous material. I can filter this down even more. So let's take something that has a fairly high suspended. So as you can see in these cases here, you have you can see the absorption characteristics of the space in this small thumbnail over here. But if you want more information about the material, you can click the thumbnail and you get this up. And here you can read which parameters went into the actual generation of this material. As you can see here, this porous material had some flow resistivity and has a density. And here you can see the complex reflection coefficient at normal incidence. So this is the thing that's actually being applied behind the scenes. I'm just going to select this one. And for the tables, let's go with wood. For the door, let's go with a door. Let's take this holocore door. The chairs, here it's easy to go to the furnishing here. And let's just do leather covered upholstered seating. And the monitors, just going to select a 20% absorbing here. And let's do plywood paneling. Okay. As you notice here, now we've gone through the whole material assignment of this model. And as you can notice here, then we also have a category here which is called scattering. One caveat with this scattering is that this is only applied for the geometrical acoustics part of the simulation. And this is also where scattering is mostly, when we talk about these different frequency regions, this is also where scattering is usually most prominent, at least when you assign a scattering coefficient like this. We have some standard ones here for these different, but in this case here, I'm gonna bump up the chairs a bit, the monitors a bit, and these cabinets a bit. We'll assume that there's a lot of stuff on these. So this is something you can adjust, alongside your material. So let's move on to the sources and receivers part here. So here you see the sources and receivers tab in the sidebar here. You can add two different types of source, or you can either add a source or receiver. And I'm just going to actually start by adding some receivers into the space. So this is your microphones or listening positions. You can place these by, like I did here, just dragging them around using the arrows. I like this little one here where you're just dragging it along the height plane. So you're just essentially moving it in 2 dimensions in the space, and keeping the set direction here the same. But you can also just set the coordinate here. Let's just add a couple into the space like this, just for demonstration purposes. Let's do another one all the way here in the corner. All right, and then that's it. There's no additional settings here for the receivers. Well, one thing you could add a little label here so you can recognize it later. So if it's just maybe in this case here, these are all listeners. So let's just call it listener 1. take this one here as like seated listener. All right. Let's try to add a couple of sources into this space as well. So for the source, we have a very similar assignment pattern here. You know, you can drag it along and you can type in these things. But for the source, we have an additional property here, which is the directivity pattern. So in the case as it is today, we have only 2 patterns in here. And as you can see here, it's only applied actually for the geometrical acoustics. This is something we're working hard on to get the wave-based part of the solver as well to generate these, the patterns. But here, for example, you can see the pattern of this, in this case, is a small 2-way speaker. And I'm just going to use that. So when you select this, you also have a selection here where you can choose which way your speaker is facing. So in this case here, let's just put this at a 45-degree angle, and you can see here how this is then turning. This is kind of it for assigning the materials. Let me just put a label here like directive source. And then place this other source here over here. All right. This is kind of it for this assignment of sources and receivers as well. The last tab we have here is the settings tab. And in here you have some what's it called, like presets. One is survey. The survey is a quick simulation, and it's only using the geometrical acoustic solver. So this is if you just really want to kind of tune your materials a little bit, you just want to see how is this looking, then you can just run a quick one of these. The default here, we try to estimate this transition frequency that I was mentioning before. So in this case, we are estimating that this should be 448. This is related to the Schroeder frequency of the space. And if I then click the estimate simulation here, what is actually going on behind the scenes is that it's doing this discretization of the air volume in here. This should only take a couple of seconds to finish. And by doing that, it can also estimate how long this simulation is going to take. So running this simulation in this space up to 448 Hertz is going to take us just a couple of minutes. I'm going to just bump this into advanced here, and I'm going to take it up to and including the 500 Hertz band, and try to estimate that so you can get a feeling for how this kind of evolves with frequency. It's going to take takes a little while, but not too long. So then we went up to 4 minutes, and we can try to estimate the 1 kilohertz here as well. And at this point here, we are going up to 1420 Hertz in this room. The estimation takes a little bit longer now, but it should only be a handful of seconds more here before we get a result. So in general, we're discretizing. When we double the frequency, we have the required size for the what's it called, these small elements here. So that means that we're increasing in 3 dimensions, which is a factor of 8. And additionally, there comes that we have to do a smaller time step when we do the actual simulation. So that means when you double the frequency in general, you have a factor of 16 to the simulation time. And this case here is going to take 33 minutes. I'm just going to go with the default simulation on this one. Which now jump back to 1 minute. And here, when I click the run button, you see here that it's estimated to take 1 minute, and it's estimated to take 0.42 simulation hours from your account here. So I'm just going to start this. One of the things that we would really like to get with this tool is kind of that it fits into the what's it called, the design workflow of designing these acoustic spaces. So I'm just going to jump back into SketchUp here to try to prove that point a little bit. And now I'm going to attempt to do some drawing in SketchUp. Now that time is not on my side here, but let's try this anyway. So I'm just going to try to draw in some partitions in the space. So in this case here, I'll draw some fairly high partitions here, 0.8 meters. Here it is, 0.8. There we go. So now I got my new partition in here. I can select this, and then the only thing I have to do to add this to the model is that I have to create a new tag here if I want to assign a new material to it. I'll call this partition, and then select this this group here, and now it's untagged. I'll just move this in, and I can of course try to copy this around the space. Something like this. Let's just do a couple here, just to spare you for the details here. There we go. Okay, and these, since I made a copy there, they are still tagged with partition. So I'm just going to run a check of this model, and it seems to be happy. So then I'm going to upload a new iteration of my design here. So I'm going to call this with partitions. I'm going to upload this. And as you can see, then I can pop this open in the Treble tool. And here you go. So if I go back to my office project here, you can see that there are two different simulations going here, two different models going here. So one initial design and one with partitions here. I'm just going to pop open the with partitions model here, and I'm going to show you how to create a new simulation and pull over the kind of the bulk of the mapping of the materials as well. So when I click a new simulation, I don't create a completely new simulation, but I can duplicate the settings from another model. So in this case here, I can select this initial design that I made. I'm going to call this with partitions. And when I add this simulation in, you can see that most of the materials actually got pulled over. So I'm going to see if we have we actually do have a partition material here. This is something I actually created myself. It was not supposed to be here. But one thing that I mentioned before is that you can also create your own materials in the space, in the material library. And you do this by clicking this little plus button up here. So I'm just going to try to pull this up and demo it for you guys. So if I didn't have a very good partition material, I could simply create it myself. Partition demo, I'm just going to call it. And let's make this somewhat porous. I'm just going to type in some more or less random absorption values here for each band. I don't know if this makes any sense, but let's try it. So let's put that here. And once I've done this, I will start a material fit. So it's not completely certain that the material, the absorptive properties that you put in is actually going to be the ones that come out in the tool as well. So as you can see here, we set a target with this, and then we get a resulting absorption coefficient of this. So what we're fitting is this complex reflection coefficient or surface impedance, and this of course has some absorptive properties that we're then kind of comparing back into what you put in. So in this case here, I'm just going to accept that it's not perfect. In this case, it's going to be fairly a much more kind of smooth line here, and you can of course tweak this and edit it back to get the properties that you're looking for specifically. I'm just going to create this material and assign this straight onto the partition here. And as far as I remember, this cabinet here. So since this was now split up into two surfaces in some cases, it has to be reassigned with these materials. But everything else in the simulation got carried over. So all the sources are in the right position. the default settings are here. Well, actually, this needs to be set up to 710. I think that was where we placed the other one. But the sources are here, and the directiveness of this source is also carried over, so you don't have to do anything to set this up. All right, so if I click here on my recent simulations, I can see that my initial simulation has finished. And we can open this up, switching back over to the other one here. I'm actually going to just throw in a new simulation here, just duplicating exactly the settings that I had here. Let's just say this is with a hard ceiling. And I'm just going to be wild and make another one, which is like another ceiling, just to show you. So I'm going to take the hard ceiling here, and let's just put a gypsum board in the ceiling. It's not a great design. And let's take the other one here, the other ceiling, and put something that doesn't have just a different acoustic ceiling here. See if I can find something that's a bit. So let's pull up the porous materials. Let's try this one. Tufted sheep wool yarn. That's gonna be nice. Okay, so what I can do here, because it's in the cloud, is that I can just take this simulation. Let's get these advanced settings set up. And I'll just go ahead and run this, starting the simulation. And as you can see here now, this is kicking into gear and the simulation was started. Then I just switch to my another ceiling here. I'm gonna set this also to 710. And I'm gonna start this off as well. So at the current time now, I have actually 3 simulations running in parallel, and it's all running in the cloud. I could shut down my browser and log on to my grandma's computer, or and I could see the same status there. So as you can see here, when you pull up the recent simulations, then you can see the progress of these. Oh, maybe I didn't actually get the one with the partition started. I'm gonna go back here. I think I forgot to press the start button actually. So, okay, now this is running. So let's go back again to my initial design where I had a simulation that was finishing. So now these are just running behind the scenes. And as you can see, it's going to be a couple of minutes before they finish. So when I click this, select the initial simulation here that I have, I can, I now in the bottom here have the ability to view the results or go into the auralizer. So let's start by just picking out, opening up the results. So in this case here, you see the overview here that you have these different cards here with the different simulations set up. You can choose here the source, you can choose the listener, or sorry, you can choose the receiver, and you can choose which type of the results you want to look at. Then below here we have these different types of curves, the parameters results, and the kind of curve results here in this case. For the parameters, you can look at these classic acoustic parameters. We have implemented this set now, and there will be more coming in the future. And you can easily switch between these two. On the other side here, you can look at the EDC curves, and there is a selector down here in the bottom where you can draw out here to get all of the bands in the same, or you can just select a single one if you want to look at the 2 kilohertz, for example. We can look at the impulse response directly, and we can look at the frequency response to look at these things. But one of the things that we've added here is the ability to compare your different simulations. So in this case here, it's always fun to look at what did the wave-based simulation do and what did the geometrical acoustic simulation do. So I can just add in a comparison here. And if I switch my first one here, the result type to the wave-based, then I can switch the other result type to the geometrical acoustics. Here you can see that geometrical acoustics actually ran from 125 all the way up to 8 kilohertz. And you can see that there's some discrepancy between these two results here, its transition frequency. We have a lot of details in this space, so probably it would make sense to push up the frequency just a little bit. But then you can compare all these different parameters and all the plots in this other one here as well. It makes more sense to just look at a single frequency here. So the 250 band, for example, where we see a big difference. And this is expected. You can compare the impulse response as well. Here it makes sense if you want to go into detail. You can zoom in, you can see what's going on here. There's of course a lot more high frequency content in the geometrical acoustics simulation rather than the other one. So I would probably mostly look at this just in a singular one where you can see these reflections coming in. But as well here in the frequency response, you can really see the wave-based simulation where you can see the room modes popping out here at the low frequencies. And you can use the zoom, and you can get back with the auto scale button here, and you can zoom in to take a look closer. Right, so I'm just going to jump back here because as you can see we're running a bit out of time, because I really would like us to look at the auralization as well. Right, so here you can see that now it popped in that one of my other simulations finished. This one with the hard sealing. You can see here that now two are done, so that's great. We can start comparing things. If I open this one up in the auralizer, simply this panel here pops up. The only thing I have to do here to start auralizing a simulation is I have to select the sound, and this one here, the directive source. Let's say I think I put a loudspeaker in here, so let's just put in good old drum loop, and let's see some high energy clapping. Maybe not a single clap. Let's use this. So hopefully, when I press the play button here, then you'll be able to hear the sound. And when we're not actually going into the space yet, we just hear the anechoic sound as it is. I hope you can hear this sound. All right, so then when I click here and I jump into a listener position, I can just click in the view here, and I can move my head around. I can see these different sources in the green and the other receivers in the blue. And then when I click the play button here, I get this spatial audio experience. There's a clap that's coming from here. I can recommend you guys to use the use headphones when doing it. As you see that this now we're getting a bit closer to the directive source. So one super cool feature here is that you can add in another comparison simulation. So in this case here, we have the hard sealing completed already. And I can switch between these two. Here you can see that the visuals of the space is changing as well. Let's hear how it sounds. So this was the initial simulation. And I'm switching to the hard sealing here. Noticeably more reverb on the Okay, I think for the sake of time and for the sake of just getting to a couple of these different questions that has popped up, I think we will go into a very shortened Q&A session here. I actually don't personally have a back end here at 10 o'clock, so we can extend it a bit further to get to the questions. I'm just gonna pull up the Q&A here and hopefully get to these the questions. Right, so we have a couple of questions here. Let me just try to sort this out a little bit. Right, so Dirk is asking here, how can I feed the material database that he already has with his own products of absorbers? And as you can see here, there is this fitting flow that you have to go through. So there is a bit of a kind of a hurdle in this. This is something that we've been working on and kind of thinking about to kind of be able to pass this over in bulk, and there will be some kind of acceptance of you and some building of a material library in Treble. So again, a question from Dirk here. Do you have tools for equal measured rework time to the model? If not every material absorption is known. Not at the moment, but you can use this this feature that I was displaying before here in the settings. You can choose this survey simulation, and then you can go in and very easily change the materials to get to another kind of get a quick feedback loop in kind of tuning in your materials. One thing with regards to this is that I would like to show you actually is that when you have run a simulation here, here is the kind of the overview of the simulations that live underneath this model iteration. So when you go in and you take this, and now this has a run simulation on it, and one of the things that can get a little bit misunderstood here is that when you then start and edit this again, if I, for example, my monitor should be 30% absorbing, I can assign this, but what I'm getting here is a warning that I'm editing this simulation, which I already have run a simulation on. So I'm kind of changing the kind of underlying settings that was this simulation. I can confirm this, and in this case here, my results and my auralizer get blurred out. But I can then change what the result was underneath this, and I can run this again here, or I can revert back to the original settings to get the result and auralizer buttons here as well, and the original 20% absorbing material here. So that's an interesting and an important part to know here, that you have this kind of edit mode when you edit a simulation that has already been run. And we're working on, in this case here, to get in a feature that, instead of just editing the simulation, you also have the ability to duplicate the simulations from right here with this new setting that you placed, so you don't have to go in through this flow here of adding a new simulation, duplicating the settings, and then reassigning your materials. All right, another question from Dirk here. Let's see. So I've noticed that you take one value of scattering for the simulation. Yeah, and this is very frequency dependent. So one thing that I would like to point you towards here is the documentation. So in the user guide here, there is some documentation about how this is done behind the scenes, because it is indeed putting in one value, but this one value is hiding some information as well. So let's see if I can find where this actually is. So in the assignment of materials here, you can see the curve here that is actually being assigned. So the value that you assign, that's what it is at 700 hertz, as far as I remember. And then, for the rest of the spectrum, we apply this this fixed curve for each of these values that is put in. So that you can see in the documentation what is being applied. And then one here from Michael. Is the reference point for sources and receiver positions always red, green, blue cross? Yes. So the reference in this case, sorry, I'm just going to try to move this on out of the way. In this case here, you always have the global coordinate system as you had it in the SketchUp model. And as far as I remember, the red one here, that's the x-axis. This is the y-axis, and this is the z-axis. I hope this answers the question. So you can always just move along these. But one thing I would like to point at, again, kind of is this, you can select here and you just drag it along a plane. And another question from Dirk, is the complex resistance of boundaries if the angle of incidence is taken into account? Yes, it is in some sense. Well, what we're assuming here is that we have a locally reacting material, which means that the kind of what we're mapping from is a random incidence absorption coefficient. We're mapping that into a surface impedance, and this surface impedance is what's it called? And that has its angle dependence kind of built into it, but it's not a custom one. It is this following what's called, maybe I'm wrong here, but following this Paris law. All right. Is a more detailed solution available than octobats? There, in some sense, you can always go into the results and you can download the impulse responses. Here in this case, there are two types of downloads that you can do. So you can download the parameter values in Excel sheet, and then you can download this package of impulse responses. And here I'm just going to pull up what this entails. So here is like source 1, receiver 1, receiver 2, receiver 3, 4, and here you have both a let's see, you have an impulse response, a monaural impulse response, and a spatial impulse response. So this is one channel, this is 9 channels. And if you want to go in and do some narrowband acoustic parameters, you can of course use this as you would use any other measurement and get these results there. But so no, it's not in the Treble tool, but it's available for your analysis later. Are material names available in other languages? Unfortunately not. We have just English as the main language in the tool. All right, here's another question from Miguel. Are the sound files in the auralization mode anechoic recordings? I would say they are recorded in an anechoic chamber. So yes, they are as they are kind of presented as such, but we have noticed that some of them are not perhaps perfectly anechoic. This is, after all, kind of an experience situation. You can always go in ahead and listen to the anechoic recording itself. If you just select something here and just press play without going in, then you should be able to listen to it here. This is apparently a very low energy one, but here you can see the clapping, for example. So you can check this out. Okay, are the tools for matching measured impulse responses with simulated? Matching surface conditions till 2 impulse responses will match. And I think I answered this earlier, that this is unfortunately not something that we built in for now, but you can use the tool to kind of do this manually. Philip is asking why it's in 32 kilohertz and not in 48. I can tell you that this is due to the fact that we don't have any content in the simulation above 12 kilohertz. And then we were just, I guess, fairly cheap on storing this. If we store more than 32 kilohertz, it's not really, there's no information in the wave file above that, so that's why we've done it. I think it should be fairly simple to convert 32 to 48, but there will be, of course, no content in it. Then Jameson is asking if the tool can be used with a VR headset. And then the question to this is unfortunately not yet. This is something we have been scoping out and working on, but it's not really in the kind of near-term roadmap. We found that most people are actually they find it most useful to just have this 2-dimensional or kind of game view, and then they have the ability to move around, or at least move the head around and get this sense of immersion pretty well on a 2D screen. But the headphones are super important here. I would say I would always recommend like over-ear headphones for this. I think in general get the best experience from that. But I think headphones, if you use headphones and not computer speakers, then you'll get a much better experience. Okay, and we have a question from Unush. A question on scattering coefficients. How much detail we should be including in the SketchUp geometry? And that's a very good question, actually, because it really isn't a good answer to this just yet. It very much depends on what you're trying to model in space. So, in this case here, we're trying to model an open office, and the bulk of the kind of acoustics, the things in the room that has an effect on the acoustics is a lot of these desks in this case here. We're trying to model the zonal differences between these different kind of aisles in the space here. Then we need some detail on the these. For example, here we've added the computer monitors in as a detail, and I tried to model in the partitions here, and in the example that we didn't really kind of follow through. But the details that you want to study, you should model those in, but you should keep in mind that if you model them with too fine of a detail, then it can impact your simulation. Exactly. So Benoit asking if there's any other 3D software besides Treble on the roadmap. Yes, we are working on what's it called? Just a generic importer, so a DXF file, for example. And besides that, we're working on Rhino, and not least, we're also working on just a generic IFC import, which will enable you to import a whole building, for example, and they will be split up into spaces, and hopefully in time we should be getting to this automatic geometry simplification, which will limit the need for actually modeling or remodeling spaces. We hope to get there in the near future, meaning sometime later this year or in the beginning of the next year. All right. Spencer is asking, for accurate STI results, should the source type be omni, or should it be speech type source? So the only difference between these two sources is actually the directionality pattern. So if you choose an omni source, then you will have then the calculation of the STI will be done in the correct manner with the speech spectrum being used as well. Owner is asking another question here, whether it's going to be possible to export video. And this is something we're working on at the moment. But for the time being, I think we've encouraged people to use just screen recording tools to get this type of a shareable experience. All right. I'm sorry for going over time here, guys. I can see that there's still quite a few participants. So I'm just going to keep going through the questions here, and I think we're gonna get to the end. If you have any more questions, just throw them in here. Jameson is asking, is there a method to calibrate the sound levels so that the listener experience can be relatable to an actual space rather than just having A/B comparison? So in this case here, you have this. You have the mixing fader here, so in that way you can do it relatively to the different things, but the thing is that these anechoic sounds here are not exactly calibrated with like a sound power in mind, so this is going to have to be a little bit of tweaking to kind of design the soundscape a bit for the auralization. Here's a question from Daniel. Are there plans for 2D plots? And yes, I can show you a little bit the roadmap here afterwards. I was kind of planning on doing that, but the time is not on my side. Let's jump into that a little bit later if you guys have the patience for it. So I agree with you that it makes a lot of sense to be looking at speech intelligibility and also the STI from a loudspeaker, and just kind of coverage plots across an audience with these 2D plots. And this is something that's coming. Then we have another question here. Since the calculations are hosted on Treble's backend, how are the details of simulations stored with regards to privacy, confidentiality, etc.? And here I can answer that we are fulfilling standards and have are working on kind of ISO certification with regards to this. We are using other third-party tools to store all this, and this is all encrypted and all this. If you have more detailed information, want more detailed information about this, please just reach out and we can share this. Costas, thank you for the presentation. Yes, we can make if you want a recording of it. You can it can be made available afterwards. And here is another question from Dirk, also related to the cloud. And like I think it's the same question here. You're very welcome to reach out to get more information about this privacy policy of ours. And Costas is asking here again if there is a good strategy on selecting the transition frequency. And like I said, this is something that is, it's a new design parameter for the acoustic for the acoustic engineer, essentially, or maybe not design parameter, but parameter in setting up a simulation. And again, here you will have to think a little bit about, or imagine a little bit about what are the wavelengths of these phenomena that I would like to model. So, for example, if you have a column in the space and you want to model how things are propagating around this, you should think about the wavelength of that, the kind of the radius of the column, for example, and have this wavelength be comparable to the transition frequencies, essentially. I think we've gone to the end of the questions here, so let me just briefly show you guys the roadmap slides. All right, so going back to the presentation here, I think this can answer actually some of the questions that we've gone through. So we're going to make a publicly available roadmap. This is just in a draft state at the moment, and the roadmap is of course what we plan to do, and we try to be as specific as possible, but of course with the caveat that these things sometimes take unexpected turns, and things can take longer or even shorter in some cases. So, but let's just dive into it here. I can say here that some of the things that we have in the very near term here is, like I mentioned before, these type of surface receivers, so 2D plot of the sound parameters in this case. Oh, sorry. And that's something that we are working on now, and we have a kind of internal version that is close to working. So we expect this to go out sometime in June. Additionally, we're working on increasing the robustness of these geometry checking steps that we have in SketchUp to make it more forgiving, so that you don't have to be working tirelessly to find holes in the model. And additionally, we want to take this results viewer that we have and integrate this into the web editor here. And by doing this, you will be able to see the points on which you're visualizing the results, so kind of plotting the parameters. So you can always have this this relationship between where is this point actually, where is this receiver that I'm looking at results for, but also the settings that went into running these simulations will be visible for you. So we're excited about that. Kind of going a bit further into the fall here, we're talking about improving the auralization. The first step in this, from our side, is to load your own sounds. So just we've gotten this, this request quite a lot. That a lot of the sounds that we have are in Icelandic, and we made this on purpose to kind of give it kind of a babbly characteristic. But I realized that we realized that of course you want people are working with this all over the world, and they want to relate the auralization to the spaces that are actually designing. So using sound bites from that makes sense to the space and to the language, also to the builders and collaborators. Then moving on to the results viewer part 2, as we call it here. Then we want to add more parameters in here to kind of encompass all of the standards that we can. And again here as well, third octave band results for the wave-based part. Then moving into Q3, generic import of geometry. So I think to begin with, it's going to be a DXF file, which is widely, it's possible to export this. And in the tool, you will then get the feedback, or if there are any holes in the geometry and so forth. The same as you would get it in SketchUp. Let's see. All right. So, and then moving further into the folder, and I think the first initial importing of an IFC file will hit the tool. And this we think is a super important part. So in the IFC file, you have the whole building model, whole model of the building, and usually this is split up into spaces or rooms, as it is in Revit if you export from there. And in this case, you will be able to import this file, and in the dashboard view, you'll just get, this was the IFC file. Here are all the spaces, and you're ready to run a simulation on each. You just need to assign the materials that was already characterized in the BIM model, and place sources and receivers in the space. And moving on here, like source definition overhaul, meaning that the ability to kind of adjust the spectrum of your sources, as an example, and setting up this in a much more detail. And kind of very closely related to that is directive sources. For wave-based, we are hoping to get this in as soon as possible and expand heavily on this database of directivity models that we have there. One thing that we're very excited about is actually harnessing the power of the cloud to a much greater extent by adding collaborative features into the tool. Right now, you have an account in the tool which is organizational wide, but right now you have your own. You don't have an account which is organizational wide, but you have your user under an organization, and we want to be able, for you to share your models across your organization. We want you to be able to share your materials, your custom sounds that you're uploading into the tool, and so forth. We think this is quite important. This is something we are, we're planning. This is very, very, very next steps for us to start working on this, and it has been planned out and architected. Moving into Q4, then we're talking about material upping kind of the material generator, so you get more options there. A Rhino plugin. I'm moving just to the next steps here. Then updating these surface receivers so that you can get this single frequency view for the wave-based part, so you can see the modal patterns in the rooms based on your loudspeaker, and what is the single frequency response of that with the room in context. Improving the auralization further. So one of the things that we're really excited about here is that you should be able to create this shareable auralization. So that means that you as the engineer would set this up in and tune the levels of the sound sources and tune the sounds and make this sound design basically. And then from there on, you could click the sound button, the share button, and you would get a shareable link that you can then share with your collaborators on the project. They don't have to have a Treble account or anything, so that they can jump in and jump between receivers, switch to these different iterations of the design that you set up, and you can get on the same page and communicate acoustics quite efficiently. Additionally, here adding ambient background noises and loading custom HRGFs. Then, kind of when we're looking into 24, and we should have a backend that supports importing your own directive sources. So from these open source file formats that is as possible, working for both the geometrical acoustics and wave-based. a Revit plugin. Now we're into the future here, so these of course have more uncertainty to it and can be up or down prioritized. Then we're talking about wavefront animations. So since we do actually have this information in the wave-based solver, it's a time domain solver, but it's all about kind of packing this into the right format so that you will be able to see the animation of the sound of the wavefront propagating through the spaces and interacting with objects. And then transmission through objects is a big thing as well. All right, and I think the last step here that we put on the roadmap, and this is just a draft at the moment, is to improve our auralization capabilities even further, so that you should be able to define this a listening plane, and the user would not just be able to move their head around, but also just be able to move around inside of this plane. All right. I think this is the end of the program here, only 25 minutes late. But I hope you guys got something out of it. If you have further questions or just comments to this, I think you're very welcome to just reach out. One thing that I forgot to show inside the tool is this very important button down here, the support button. If you pull this up, you can file a support request, and this is, please just do this as much as you can, just use and abuse it, and we will be very quick to get back to you with a comment. If you find a bug in the tool, please report it, and if you have some requests for things that we should be bumping up and down in the roadmap in the future, please also file these in. We are very susceptible to these types of requests, so it might actually end up with you actually getting what you're wishing for in this case. We at least sincerely hope so. But I think with that being said, unless anyone has some closing remarks to the Q&A, I'm just going to leave this open for another couple of minutes here. But then I think it's done from my side, and I'd just like to thank you all for listening. It seems like we still have some 20 people on the call, and I'm really happy that you had the possibility to stick around. So apologies for kind of extending the webinar a bit. Okay, thank you very much, and I'll see you next time.